Hello and welcome to the course Design Bore Fields with Confidence. This is part 1 of the course, chapter 3, where we will talk about the input parameters you need when you're starting to design your bore fields. And in this first chapter of these input parameters, we will be talking about the ground properties. Now, when we talk about ground properties and geothermal design, there are basically two properties important. And that's on the one hand the ground thermal conductivity, and on the other hand the ground volumetric heat capacity. Now, the ground thermal conductivity, the lambda value as often referred, is a measure of how well the ground conducts heat. Basically, when you put energy into the ground, how fast gets it dissipated into the environment. So that's one important element. And the other important element is the ground volumetric heat capacity. And that's a measure of how good the Earth can store energy. So basically we already talked about bore fields that are seasonal thermal energy storages. Well, that has to do with this ground volumetric heat capacity. If the ground can store quite a lot of energy, then the bore fields you install in this ground will also have good seasonal thermal storage as well. Now, when you have a very high imbalance, now imbalance is when your ground cools down year after year or heats up. If you recall our previous chapter where we talked about bore field design and why it is important, we saw that our temperature profile went down year after year. So there was an imbalance because the ground cooled down. Now, if you have such an imbalance and your ground temperature drifts to a lower or to a higher temperature, then you want a very good conducting soil, because then your heat, your imbalance get dissipated away quite easily and you don't feel this negative or positive heating up trend. Also, you want a very high volumetric heat capacity, because if your heat capacity is high, it means you need quite a lot of energy. You need to put quite a lot of energy into the ground in order to notice a change in temperature. So both a good conductivity and a good volumetric heat capacity are important when you're dealing with this imbalance. On the other hand, if you want to have good passive cooling and you want really to keep the heat and the cold as close to the borehole as possible, you want to have a very good volumetric heat capacity because you want to store the energy really well, but you don't want a very good conductivity because then your heat gets dissipated away. So that's an important difference. Now, I also want to mention that, your project location is what it is. You typically don't have the choice what the ground properties are. But perhaps if you have different ground layers, you can design your bore field in such a way that you make sure that you are in the ground layers where the thermal properties are as beneficial for your project as they can be. But this is just to show you what the importance of certain elements are. Now, there is also the factor of porosity and groundwater flow that has also an effect on your imbalance and so forth. We will discuss that later in this course. Now, here you see a table of minimum and maximum thermal conductivities and the volumetric heat capacity for different rock types. And there are other reference tables as well. Perhaps your country or your region has a local database with values where you can find these properties. But there are two things that we can notice here. We have on the one hand the solid materials, the rocks, your granite, etc. Not a geologist, but you have your solid rocks. And what you can see here is that there is quite a big range, even for the same material, let's say granite, of 2.1 to 4.1. Even for the same geological conditions, let's say. And that has to do with mineralogical properties and so forth. So even for the same ground layer, there can be quite a lot of range in this thermal conductivity. And when we look at the granular material, or sands or clay and so forth, we see that there is here also an important aspect of water content. And you can see sand as small circles, small balls all touching each other, but there are it's porous, so there is either water in between it, making it a good conductor of heat, also giving it a high volumetric heat capacity. But when there is no groundwater and it's unsaturated soil, yeah, there are voids. And as you perhaps know, a void is an insulator that can pass no heat through a vacuum. So when there is air trapped, there is no heat transfer possible. So the conductivity is also worsened. So that's also important when you're using these ground parameters for your project, that you know, yeah, is my ground saturated or not? That's also an important aspect because it determines quite a lot your volumetric heat capacity and your conductivity. Another parameter that is important besides thermal properties of the ground is the ground temperature. Because if you recall a temperature profile, it starts somewhere. And depending on your location or your borehole depth, yeah, your initial temperature can be 10 degrees Celsius or 13 degrees Celsius. And that, of course, determines where your temperature profile starts and hence also where it will end. So that's also important to keep in mind. What is your initial undisturbed ground temperature? Meaning, if I drill my borehole, I install everything. When I turn on my system, what is my initial temperature when the ground is undisturbed? Now, this is perhaps not known for your location, so what you do is, what we do in GHG Tool as well in other design software, is we assume or we know the average surface temperature at your location. And since we know there is a warm bubble inside of the Earth that's emitting heat towards the surface, there is a geothermal flux of heat. Now, depending on your location on the Earth, this can be higher or greater. If you're in a volcanic region, it will be higher, definitely. If your crust is thicker at your specific location, the flux will be a little bit lower and so forth. But the thing is, there is at every place on Earth a geothermal flux, and hence also a gradient. If you drill deeper, the ground becomes warmer. Now in our regions, that's typically 2 to 3 degrees Celsius per 100 meter, and we assume it's linear. So that's easy because when you say, okay, I'm going to drill to this depth, we have this ground surface temperature, we have a database also where the geothermal fluxes are, then we also know, okay, this will be my average undisturbed ground temperature. Now, there is a problem with this linear assumption, and that is that it assumes that there is no construction, there are no constructions on the location. Because initially, when there were no humans on Earth, the ground temperature and the air temperature, they were in balance, let's say. Now, over the years, there is this steady state condition. But then what happened is we started building cities, and the concrete and the material, they captured heat. So our average surface temperature went higher, which is visible on time step 2 on the slide. But your ground temperature was not following. But over the years, over the decades that we have had cities, this heat of these cities is going into the ground. And you see this sort of temperature bubble occurring, where the ground temperature at 10 meters under your city is still relatively warm, and the deeper you go, 20 meters, 30 meters, 40 meters, your temperature first decreases. And after a while, you still find this original linear gradient, let's say, after which, if you drill deeper, the ground still becomes warmer. So there is, especially in older cities, this problem of this temperature bubble, where if you want to find cooler ground, that you actually have to drill deeper to be able to, go to this colder ground again, which is important if you have problems with cooling or your building has a high cooling demand, because you want to stay away from this high temperature, so you want your borehole to be as cold as possible. And that's an important problem. And one way to solve it is just to do the measurements. And you can do this measurement with something which is called a thermal response test. We will cover it in more detail later this course, but basically what it is you install a borehole at a depth and the way you want to do it for the rest of your project. You're going to put a machine next to it that's going to measure the temperature going in of the borehole, going out of the borehole, and you're just going to inject a constant power into the ground. And based on these measurements, we can find the ground thermal conductivity, which is one important aspect there we call the imbalance. So that's important, we can measure that. We can measure the initial undisturbed ground temperature, so we know where our temperature profile will start in the end. And then thirdly, we can also measure the borehole effective thermal resistance. Now, if you do not know what that is, no problem, we will cover it next month in part 2 of this course. But that's basically the advantage of a thermal response test. You can measure conductivity, your initial temperature, as well as your borehole resistance. So that was what I wanted to say about the ground properties. A next piece of information that you definitely need in order to make a geothermal simulation is your building demand. What is the demand for heating, cooling, and domestic hot water that my building demands? So that's what we're going to focus on next.